Well, I started drawing this little cartoon to be able to make the case of what we've talked about so far, just to give the workflow in terms of logic. I don't expect you, these aren't particularly magnificent figures, I don't think, but what they do is they represent cameos of kind of the logical progression of what we are trying to do in terms of understanding, I guess, reality. This is the real world. We've looked at these. We'll go back and look at them. What happens in microcosm around the fronts of these? I guess this represents the behavior that occurs around these fronts. What this represents in terms of an experiment that we might do in the laboratory, in terms of its physical interpretation, and how we ultimately codify those results. And then I guess the ultimate is use it to be able to say something about this. So that's kind of the logic of what we're doing. So keep that in your mind as we go back through this. So I'm just going to recap exactly what we've talked about in terms of each of these maybe 4 component pieces. If I can find those 4 component pieces. Come on in. Right there. And so I roughly know where these things are. It's right. We go past it. There it is. So these are the 2 key figures, I guess, that we talked about before. We talked about the case where the fluid is lighter than water, in which case it will sit as a lens on top of the water that looks kind of like this. It will slightly depress the water table because there's this weight, extra weight of free phase fluid, which is 100% saturated, versus what was originally above it was only maybe 10 or 20% saturated with the liquid. Now it's 100% saturated liquid, so it depresses the water table and compresses the capillary fringe. The capillary fringe is the area above the water table where it's only partially water saturated. It's 100% water saturated at this point. As you go up to the capillary fringe, I guess it's actually 100% water saturated, but the fluid pressures in the liquid are in tension by definition. And then once you get above this, it's only partially saturated. So up to this point here, below here, the saturation of water is equal to 100%. We have this smeared zone as we come down here, which is this chimney in simple way, which you could imagine that if you drop some gasoline on the counter, you'd end up with a sheen of that material stuck to the counter. So this is the sheen that would be stuck around the individual grains that are in this column, in this so-called chimney. And then a zone around where the 100% gasoline meets 100% water just below it, and is able to transfer mass across that interface by dissolution. And so what we've been talking about is trying to understand what will the saturation look like, for instance, as we go down in this column. That'd be one question we could ask. What will the saturation look like as we keep on going down through here? And how can we predict that based on what we know? And why does it stop right at this point as opposed to this point or this point? How do we make choices about that? So that's kind of the physical system. And this, of course, is for something that's lighter than water. If it's denser than water, then we have similar behaviors. But all that now is different is that instead of being arrested in some way by the presence of this region here, it's gone right down to the bottom. It's made a lens that sits on the bottom that presumably can't get across this capillary barrier because it's the pore spaces, the pore throats are too small, that you need a really high height of this material to give enough pressure at the bottom to be able to force its way through. And so it's stopped at this capillary barrier. It's left again this smeared chimney as it goes down through here. And you might presume from this coloring that also the saturations of this denser than water component are actually larger here than they are at the surface. And you could imagine that they get to be almost 100%, although we know they can't quite be 100% as you go down into here, because there's always going to be some residual water that can't get squeezed out of it. So again, the question would be, for instance, how would, if you wanted to plot saturations as a function of depth, maybe saturations of water between 0 and 100%, how do those change as we go down through this? And indeed, does it stop? How good a capillary barrier does this have to be before it will actually stop it? Do the pore throat sizes have to be the size of the venometer, 1 millimeter in diameter, or do they have to be 1/10 of that, or 100th of that, or 1,000th of that to be able to stop it from going? And so those are the kinds of questions that at least we've partly set ourselves up to be able to ask. Right? So that's reality, if you like, in terms of what we're attempting to do. We know, we could imagine that at the interface between these, right at this boundary here, then we would see some of the behavior that we've already alluded to, and that is this diagram that we've looked at a number of times. And you can see, I think you're right. Below, this is basically the demarcation line, which I can draw on now, between relatively large particles and you can only see, on my screen I only see kind of it's kind of mottled color, but you can get some, from the texture you can see what the size of the particles are. And this stuff has easily gone through these larger pore throats. Presumably pore throats sizes are related to the diameters of the particles themselves. You can imagine a bead pack of marbles, and the spaces between them are going to be proportional, not the same as, but proportional to the diameters of the beads. And it's easily got through here under this amount of height. So it's got a thickness of this that's traveled down, and there's been enough height there to physically push it through it. But that height that gives you a particular pressure in the red phase at this point versus a slightly different pressure in the water at this point is not large enough to make it invade all of this, but it has picked out one pathway through this, which presumably is larger pore throats, which has allowed this little ganglion to develop. And you could imagine that if you boosted up this height here, what you'd do is you'd increase the pressure here, just like the pressure you'd feel at the bottom of a swimming pool as you make it deeper. Ignore the fact that it's in a porous medium. It's like a swimming pool that's just filled with sand. It doesn't make any difference to the fluid pressure you'd feel if you're sitting on the bottom of the swimming pool. And so if you increase this pressure or head by some amount which increased the pressure, then maybe this would just keep on going a certain amount, and maybe this would keep on going a certain amount, and maybe some boundaries here that weren't activated originally actually come up with filling up the pore space. And so that's the process that we're looking to understand. And we understand it in terms of capillary behavior. The basic idea is that the only driving force in this is the weight of the water, which is pushing down, and it's resisted by the interfacial tension, which is actually a very big force per unit volume, which is pushing back. If the pore throats are very large, there's a very heavy tube and very little capillary resistance, and so it keeps on going. If it's very small, still the head gives the same pressure there, driven by the same weight of water, but the resisting force is relatively large in that particular case, and it resists it and stops it going over. So that's the second part of our understanding in terms of this. The analog between this kind of model and what we might do in the laboratory would be our experiment for being able to figure out exactly how you measure capillary pressure versus saturation curves. And these curves here, in other words. And so the idea here is, as we looked at, if we kind of zoom back to that, is actually the same as this figure here. If you make this height larger, you invade more pore space. And so this so-called Welch apparatus, if I can find it, is on page, don't want to give you whiplash, I know it's part way through. I think it's like here. No, I thought I wrote the number down, but I can't see that it's right here. This. So this apparatus here, this so-called Welch apparatus, basically takes a small core of this soil that we had. Originally, like before, it's completely filled with water, and you surround it with this red NAPL all the way around it. And this is just connected to the exterior. And so you have a height of this NAPL which really registers a pressure in here. And you could keep on increasing the height of this column successively. And what you'd expect to happen would be exactly the same as we saw in that diagram with the invading red fluid. Initially, when it's not high enough, you don't get anything in it. When you increase the pressure enough, you'll get some little invasion on the edges, so that within these little slithers, it's 100% saturated with the NAPL, the red fluid, but outside that, it's 100% saturated with water. But if you take it on average, on aggregate, then maybe it's 5% NAPL saturated and 95% water saturated. And so that gives you, for this particular pressure that you're applying, whatever that pressure is, it gives you an ordinate on this graph. A given pressure that you're applying, a given average saturation that you have, and you have a point. You increase the pressure to another magnitude, go up, it'll invade some more, so it'll be 90-10, say, and then, so you have these two new ordinates, and you have this curve here. And so if you start connecting the dots each time you do that, until ultimately it's almost fully connected with red with a little bit of water in it, then we have basically this relationship which we drew before, which goes up to some asymptotic value beyond which we don't go. And so this is, if you like, the linkage between these two behaviors that we have here. We have an observation in the field. If you take an REV, it's a term that hydrologists love to use, representative elemental volume. In other words, one that represents kind of the average state of the system. So in other words, if you have this core and it has one slither of fluid in it, that's this red fluid, then if you take a representative elemental volume that just includes this red stuff, it's not really representative. If you take one that's this, then, well, it's still 50-50, where in reality, if you take one that is more representative of the real behavior, it gives you the appropriate relative saturations of the two fluids. And so it depends on the scale at which you're looking. If you're looking at this scale here, the scale of the tip of this, it's 100% NAPL saturated or 100% water saturated. But if you look on average at what's going on, then it's some proportion of saturations of water and NAPL, the two of which have to add up to 1. And so that's the connection with this figure here. It's representing kind of an overall behavior. And so to finally recap on what's relevant to what we've been talking about is to look at, if you like, the ordinates of that figure. This is the most recent one that the last one we talked about. And so what are the important ordinates of that figure? The fact is that the saturations of water go from 0 to 100% as you go left to right. The saturation of the non-wetting fluid is the reciprocal, goes from 100 to 0 as you go across it. This represents, what do we call this pressure here? Just shout. Bubbling pressure, yeah, great. Bubbling pressure, or PC0, it's the pressure you have to apply to push a bubble into the largest pore throat, I guess, in the system. Once you do that, then it starts saturating. We go on what's referred to as a drainage curve. A drainage curve because all the initial work in this area was done by looking at water in soils, partially saturated soils. So if you pump air into the soil, you're draining water out of it. Of course, you're draining water if you're pushing a NAPL into as well, but I guess we think more readily that drainage is just getting something out of it and not really putting anything else in. Of course, you are putting something else in, you're putting air in, but perhaps you don't think of it that way. It has an asymptotic value, and this asymptotic value is referred to as, anyone want to remind us? Great, got it. And if you then drop the pressure, thank you, you come down here and you end up with the converse of that, which is SNW0, which in the same terminology is irreducible saturation of the non-wetting fluid by definition. So we're almost limited between these two barriers, left and right, and so we'll always have a certain amount of water left in the system. We can't get more than this water out unless we boil it off or evaporate it. And we can't get, once we've invaded it with another fluid such as air or as gasoline or a NAPL organic component, this is the maximum amount that will always be left with this amount in the system after that. We made the case that these things are hysteretic, so they don't go up and down on the same trajectory because one has been pre-wetted or pre-dried, and so they don't follow the same course. And if we stop part the way in between, then we go across what we refer to as scanning curves to go from one major curve, the drying curve, to the imbibition curve, to move across it. It's imbibition because it's almost spontaneous. It's the same as, do people know what blotting paper is these days? Has anyone ever used a fountain pen ever in their lives? Did you do calligraphy at high school? No? See? Oh, geez. What's the world coming to? Well, blotting paper is just when you used to write with a fountain pen, and you used to have ink, you used to blot it so it didn't smudge, like using a Sharpie and putting your hand across it too quickly. So blotting paper, like filter paper, if you put it in a solution, there'll be capillary rise in the blotting paper, just suck it in. And so it's rocks aren't any different from that. They'll imbibe, and they'll imbibe spontaneously, which means they'll provide some suction. So the mechanism by which a front goes up, if you dip filter paper into water, or any paper for that matter, but filters paper especially because it has a certain pore size in it, the rise in that is controlled exactly by interfacial tension driving it up. Chromatography is slightly different from that. Chromatographic separation is slightly different. It's just the rates at which things get carried up and retarded, but it's also related to the stuff in this course. No different from a porous medium. So if you understand what we've talked about here, then you understand everything you need to know about multiphase flow in terms of static behavior. The arrangement that it will go to once you drop it into the ground and wait for 2 months for it to get to some equilibrium condition. It doesn't say anything about how quickly you can take it out of there, which is a different question, which we'll also address. But basically, this describes the whole workflow to be able to understand what's going on. So since this represents these behaviors, it seems reasonable to think that if we have this information here in a capillary pressure versus saturation curve, then we should be able to use that, maybe, if we know what this is, to say something about what happens in situ. And the final part that puts this together, I guess, is that we can also scale this in a certain way, very important, to these Leverett curves, which give us the capillary pressure, which I suppose we might define, is always the difference between the non-wetting fluid pressure and the wetting fluid pressure. And interfacial tension, permeability, porosity, square root. And if we draw this figure, we end up with a capillary pressure versus saturation curve, which looks something like this, just as a ballpark. This is saturation of water. This is 0. This is a 1. Do you remember what this number was, anybody? Talked about it. Yeah, 0.87. I don't remember what this number was, but I would wager it's of the order of 10%. So, incredibly useful curve to be able to just get a feel for this. We rarely, in any consulting job, measure those directly, but if you measure permeability through some easy means, typically in situ, if you measure porosity by taking samples or trying to measure it in situ, and you know what the physical properties of the fluids and solid surfaces are, which are tabulated, for instance, interfacial tension of water is what? think it's 2 millinewtons per meter, something like that. I think that is right. You'll use it in your assignments. Then immediately you can construct what this capillary pressure versus saturation curve just by scaling, and you'll get a chance to do that. Okay, so that's a recap of what we've done for the first couple of sessions. We've talked about multiphase flow. So let's see how we might use that in some useful way. So this is what we might be interested in doing. So these are the figures, the big picture figures that we drew of the NAPL and NAPL and how they might penetrate. Actually, it's not. It's the Vado Zone and an NAPL. No, it's actually NAPL. It's a NAPL for sure, but it has to be denser. So there's two conditions that we look at. One is for the Vado Zone, which let's look at first because I think it looks most familiar to what we've looked at so far. We've defined exactly what we mean by capillary pressure. It's the difference between the pressures in the two fluids that are present in the system. The two fluids that happen to be in the system in the Vado Zone, in other words, the region above the water table. So in other words, in our figure, you'll recall we had a Vado Zone, we had the water table, and we had this lens that sat on top of it. It was like this, with a chimney. So the Vado Zone is this part. Actually, it's the whole way up to the surface. I guess this is the capillary fringe. This is actually the Vado Zone. It's the whole thing. The part between the groundwater table and the top of the capillary fringe is the tension saturated zone, or the capillary zone. But I guess the whole thing is the Vado Zone. So that's right. So this whole thing is the Vado Zone. This is a cross section through it. This is the water table. This is the top of the tension saturated zone, where it's 100% water saturated because of interfacial effects. And above this, it's partly water saturated, partly air saturated rather. Below this, it's 100% water saturated. So actually below here, although we haven't defined why that should be, the saturation of water is equal to 1. I'm not sure. I think my handwritings get better, don't you think? And so how would this map out? Well, we know that if we took a portion of this, a sample of this material, and did an experiment with it in this Welch apparatus, we'd get a curve that we think that would look like this. Normal, this is just our drainage curve. As you start off with water saturated 100%, and we increase the pressure of water that we apply. Water is our non-wetting, sorry, I'm talking backwards. If we apply air in our system, air is our non-wetting fluid typically. Water, wetting. Water is often usually the wetting fluid. And so we'd end up with a capillary pressure versus saturation curve that looks like this. This is the bubbling pressure, PC0. And so how do we relate that curve that we might measure in the laboratory to what's physically going on in the field? What do we know about the system? What we do know is that by definition, the definition of the water table, which is this point here, which I always do as a little triangle with a squiggle below it, is that by definition it satisfies two conditions. One is it's 100% saturated with water. The second one is that the fluid pressures here in the water are atmospheric, exactly atmospheric pressure. And so if we do this as gauge pressure and define this as atmospheric pressure as 0, then this would be atmospheric pressure here. So this would be this ordinate here. If we go up in this, and if we draw this diagram of pressure horizontally, positive if it's on the right-hand side, if the water's in tension, it's negative. What would we expect to happen if we go below the water table? We start off at atmospheric pressure here. If we go down here, then the pressure is just going to be equal to the elevation change multiplied by the unit weight of water, just like a swimming pool, no different than that. So this is the expression as you go into it. It doesn't matter that we're going down within the pore space of a porous medium. It doesn't make any difference to the pressure so long as it's fully connected from the top to the bottom in water in a path that you can get into. If it was air-filled, then also as we went down from this point at atmospheric, if there's no water, then the pressure change would be this green line. The unit weight of air is about 1,000th of the unit weight of water. 1 kilogram per cubic meter versus 1,000 density, not unit weight. And so they scale exactly relative to each other. And so we'd expect that this would be scaled by 1,000th of this. So it's basically the axis, the horizontal line. The vertical line. If we, instead of going down, we go up, then you could imagine that if it's water in our system that we're going up through, the pressure is going to change as in this. And so the pressure that we'd experience would be equal to a tension, because this is this here, it's negative. This is equal to be close to atmospheric pressure. You can imagine it's atmospheric pressure because this green line is always going to be basically on this axis, 1,000th of the scale of the blue line. So basically this is always 0 in this particular case. And so as we go up, the pressure is going to be negative, and so the magnitude of the capillary pressure is going to be equal to this negative amount, which is equal to here. And so when we exceed that amount, which is given by this curve, all of a sudden now we're able to bubble air pressure into this system. As we bubble air pressure into here, then the saturation to air will no longer be 0, but it'll be some small amount. As we keep increasing the pressure of the air within our system, then we'll get larger and larger pressures of air trying to push into the system. Larger and larger pressures of air, not because this is changing, but because this is getting progressively more negative. So the difference between these is increasing as we go up here, and we change the saturations. And so at this point here, at this particular pressure, whatever it is, this would be the saturation of air, and this would be the saturation of water as you go up here. And so physically what this is allowing us to do is it's allowing us to track what the saturation would be as we go up here. Partially, it would be 100% water saturated until we get to some point which is indexed by this point. And only after we get above the top of the capillary fringe is it going to change to be something where it's partially air saturated and less than 100% water saturated, and progressively more and more air saturated and less water saturated until we reach this asymptote, which is this vertical line that goes down here, which we said before might be 10% of that order. Right? So that just explains exactly what we have as we go up through the system. So it's all related to the relative difference between the pressures that we have within these two individual components. The difference between the water pressure and the air pressure. Here, the water pressure is negative, equal to the bubbling pressure. Here, the water pressure is even more negative because we're going further up in this direction. And so between these two, it's giving a bigger differential between this. This essentially is always 0. And so you can see this at some places. One of I think the next example that you'll end up doing is this. Not a very good diagram, but it serves to give to make the point. These are actual measurements of water pressures above Yucca Mountain. So Yucca Mountain sits in the Nevada desert. There's a repository maybe still will be, planned to be at 300 meters depth. The water table is another 300 meters down below the repository where it's saturated. And so in total this is 600 meters, so it's about 2,000 feet, right? 2,000 feet total. So this is 1,000. This is 2,000. So if you think in feet, that's great as well. I only say that because this thing's actually written in feet. And so if you took samples from each of these components, and if somehow you're magically able to measure what the pressure was in the water that's in there, this diagram here on the left gives two parameters. It gives the magnitude of the porosity as you go down with depth, which are these individual figures here. And the porosity is around 30%. So 30% of the pore space is open, and 70% of the rock, I guess 30% of the rock is pore space, and 70% is a volcanic rock. It's igneous tuff. And as you go down through it also, the magnitudes of the saturation, even though it's so-called unsaturated material, the saturation is of the order of, it's above 80%, it's between 80 and 100%. So even though it's referred to as unsaturated, which was one of the reasons why it was chosen as a potential repository site, the unsaturated part of the rock is actually the big fractures which aren't able to take water because the water just disappears down because they're too far open that they can't hold it there. If you somehow could magically go into this and you could measure the pressure in the water, then the figure that you'd get would be this diagram here. Each one of these data points that, I won't do that because it will bring this up every time. All of these data points are a single measurement for a water pressure within this 90% saturated portion of the rock. And you'll see if you drew an envelope around these, one envelope that would almost cover these would be this red line that I've just drawn on here. And you see that this isn't a linear scale. This is water potential. You could think of this as negative pressure. Water potential is the negative, the tension, if you like, in the water within the soil. And it's a log scale. And so if you stretch this log scale out into a natural scale, what it would look like would be this. If you looked at water pressure versus the height above the aquifer underneath it, this is the aquifer which is at this depth here. And so if you look at this figure here, if you did it on a natural scale, this would be water pressure and this would be elevation. And it's exactly the same as the magnitudes that we looked at on our previous curve, and that is if you look at the magnitude of this water potential, this is basically equal to the negative pressure that it would take to take a column of water at this point that was this high, equal to the height above the water table. So in this case, I guess it would be 1,750 feet tall. And if you could hold this column of water, the pressure that you'd have to apply, or the stress that you'd have to apply to physically hold this up by its bootstraps, would be this magnitude of pressure that you're seeing here. If you have a column that is only this high, roughly 1,000 feet, then the pressure you have to apply is only this amount, and it would be equal to rho z, g, I guess. Density times the unit weight times gravity of the height of it. And so it's not saying anything other than that this curve is a linear curve of pressure versus elevation. And if you go back to this curve here, it's no different. We've just drawn it a slightly different way. It's no different from this curve here. And so it's real. I guess that's the only point I'm trying to make. And you can measure these things. And you could, the reason that, well, let me ask you, what's the reason that, what does the fact that it's 100% saturated at very high elevations close to surface mean that the PC curve would look like? What would you expect this capillary pressure versus saturation curve to look like? Would it look like the one that's drawn there? Would it look like this one? Or would it look like this one? What do you think? And how do you rationalize it?
I would say it looks like the bottom one, probably because the water's moving downwards.
Yeah, but this would mean that, so now this would mean that if you're this high, that you would be 90% air saturated and 10% water saturated. And so, but we know that in our actual system that we're basically 90% water saturated and 10% air. So does that change your mind of what it might be? Okay. Yeah, that's right. So that's this. So to do that, it has to look something like this, right, at least. So it means that it's pushed this capillary pressure curve up. So it means that to be able to do that, so it is able to capillary rise all the way to surface almost at 100% saturation, it means it has a really, really high entry pressure. And from what we know about entry pressures, What's our relationship? PC0 is something like 4 times interfacial tension over diameter. If we know this from what we said before, if we know that this is the capillary pressure, we could also, what could we do? We could divide this both sides by unit weight of water. We know this. We just said this is 2 millinewtons per meter. So we know this is 2 millinewtons per meter. So we know this interfacial tension is 2 millinewtons per meter. Actually, why don't we do the calculation? We know it's, what do we know? We know that this term is 600 meters. So let's rearrange it. So what is that? D, we can get the pore diameter out of this. D is equal to 4 times 2 times 10 to the minus 3 newtons per meter. That's this. Put D up here. We put 600 meters on the bottom. 600 meters is 1,000 meters, right? Near enough. And the unit weight of water is 10 to the 4 newtons per meter cubed. I think the unit should be right. And so, does this give us a reasonable number for that? What would it give us? It gives us 2 fours are 8, which is really 10. So it's 10 to the minus 2 divided by 10 to the minus 7, right? 10 to the plus 7. So that's equal to 10 to the minus 9. Probably about right. It says that the pore throat sizes are about a nanometer in diameter. So they're certainly submicron, but they're tiny, right? So they're tiny. So they're so small that they're able to physically hold that water in there because the meniscus forces are absolutely incredibly large. And they must be, right? If you imagine, I don't know if you ever, perhaps you don't think about it, but if you think about 2,000 feet of water, 600 meters, so it's the water. Most watches are rated sometimes, is it 30 meters or 300 meters? I can never remember. It's one of the two. So 100 meters of water is a big, big pressure. I'm not sure it's a pressure that we necessarily as humans be able to survive. So if you imagine taking a column of water that's 1,000 meters high, 1,000 meters is top of Mount Nittany down to no, it's 1,000 feet. So it's 3 times the elevation gain between the valley bases and the tops of the crests of the ridges around here. So it's a big number. So it's interesting that this can maintain being fully saturated as you go towards the surface. Actually not quite, right? Because these data aren't at the surface. But all the way to this point, it's almost fully saturated as you get up to the surface. Because this curved line is basically this reorganized straight line. Right? Okay. Well, I'm going off on tangents here, so we're not going very fast through this, but that's fine. So if you imagine this now for the case at hand, for the opposite case, instead of the case where we have the Vado Zone and we look at a DNAPL going into the system, the same behavior applies. Perhaps it's easier to visualize. You have a DNAPL, which in this case is our green component here, which has a ganglion that goes down. It's denser than water, and so if you look at the pressure change as you go down, so long it's simply connected, it'll again increase in pressure more quickly than water. If you go down through the water on the outside, then it will increase in pressure more slowly. By definition, even though I've kind of covered it up, our definition of capillary pressure is this. In the same way that as we went up here, the difference between the now covered blue line and the green line is the capillary pressure here. This is the capillary pressure here. The difference between the pressure in the non-wetting fluid and the wetting fluid. And as you go down, perhaps it's easier to see here. It starts off at 0, the difference between them. As you get deeper and deeper down, it just grows linearly. So this would scale linearly as you go down through here with depth. So the capillary pressure scales with is proportional to depth. And you see the same behavior. This you'd expect to be 100% saturated. Below this, 100% saturated with the NAPL. And this would be partially saturated. Partially saturated with each of the two phases. So now this is the saturation of water, and actually, and this is the non-wetting component. Because the difference, am I doing that really? Do I really? Yeah, that's right. Yeah, it's actually not the best example, so it doesn't matter. But the relative saturations of these will change in proportion to the differences in pressures between these. And so that's why you'd expect that as you went down through this, then you'd end up in this particular case. I guess I'm drawing the case for a lighter than water system. So this would actually be, screwing this up, I guess. This is water. This is water, and this is non-wetting. Because now we're applying enough pressure to be able to get water into the, there's not enough pressure to be able to get the NAPL into the system. Above a bubbling pressure, we're able to get enough of it into the system that now all of a sudden there's a small proportion of it here. As the difference between these two pressures gets progressively larger, it's possible to get a larger and larger proportion of the non-wetting fluid into here at the expense of the water which it's moving out. And so as a result of that, you end up with the saturation profile as you go down through the system being defined. Okay? And so that explains really why we have those the two behaviors that we drew in Cameo, that you have a portion which is this smeared zone, a portion which is partly NAPL and partly water, and a portion that is 100% water, 100% NAPL at depth, as it hits this barrier and can't go beyond that. And so it allows us to be able to put together from these capillary pressure curves exactly physically what's going into the system. All right. Okay. So I guess we didn't really start off in that. So we're interested in being able to say something about the geometry of this, and I guess we've already dealt with part of this. Let's look at it in a more simplistic way. And one question that we might want to ask is whether, for instance, if you take a salad dressing, which is oil and vinegar in a bottle, and you have the lighter oil sitting on top of the denser vinegar, I think that's the way it goes, right? The oil is less dense. Whether it's feasible for it to sit the other way around with the more dense water, vinegar-based water, on top of the oil. And the answer to that question is there's no intrinsic reason why that couldn't be the case. If you took, for instance, one fluid that was denser than another and you put it on top of the less dense fluid, there's no reason that if you look at the force balance that exists, that they shouldn't be able to sustain that. And the rationale is this. If you go down through this fluid to this interface and look just above this interface, then the pressure of this interface would be equal to its depth multiplied by the unit weight of the non-wetting fluid. And if you look at the fluid pressure that would exist immediately below that interface in the other fluid, would be the pressure would be equal to the height plus a very small amount, again multiplied by the non-wetting fluid. Actually, it's not quite true, right? You'd have to add another portion for the wetting fluid below it. So I guess it should be written out as the pressure would be equal to the height times the unit weight of the non-wetting fluid plus a small change in that height multiplied by the unit weight of the wetting fluid below it. And so the idea is if you make this DH really small, so they're basically the same point, but just on the other side of the interface, the pressures are the same. So they're in equilibrium, so it shouldn't do anything. So the problem happens if you went in and you physically pulled down this surface a little bit, so that instead of looking like this, it looks like this. And now if you do the same calculation, you end up with an imbalance. You end up with an imbalance because the pressure acting at the tip of this little dent here is given by the height down to the bottom of that dent times the fluid. But if you go in this fluid here, the pressure at this point has to be the same horizontally all the way across here. And we know that the pressure at this point over here has to be this height of fluid times this unit weight plus this height of fluid times the other unit weight, which is less, right? Because it's a less dense fluid. And so if you do the sum of these two, you find out that the pressure acting downwards is less than the pressure reacting against it upwards, and it physically can't sustain it. And so that's really the only reason that it can't do it, is that if by some irregularity you end up with this little divot, the imbalance is a positive downwards, and so the divot grows, gets bigger. As it grows, this driving component gets larger and larger, and this component here gets larger and larger because this is denser than this, and therefore it's unstable. And so that's the mechanism by which it occurs. And so there's no theoretical reason why you couldn't have a more dense fluid sitting on top of a less dense fluid, but the reason it doesn't work is because it's physically unstable. The same as if you take a kitchen bowl, turn it upside down and put a ball bearing on the top, it wants to find lower potential and it will roll off anyway. If you turn the bowl the other way, to be able to move sideways and down, it has to move up across the lip and out. And it's in kind of a force well, or not a gravity well, but a force well. So what we could do is we could try applying that not to the case where you have two fluids on their own, but you have two fluids with porous media. And so the case for that would be if you now take a porous medium which you saturate to the surface with water, and you take a 55-gallon drum on the surface, and you put something in it such as a NAPL. And now if you do that, then you look at the pressure that that column of water would apply right at the surface of this, and you can do the same calculation. And basically ask in the case, if you put a height of this here, does it stay within this barrel that has a puncture in the bottom, or does it go into the subsurface? What are the conditions required for it to go into the subsurface? And then I guess the final condition is, if it does go into the subsurface, where does it stop? Does it stop here, or does it stop here, or does it never stop? What are the conditions that control that? And so we can do an analysis which is basically the same as the other one that we just did 2 seconds ago. And that is that we look at the interface, interface for whether it can get into here. It will go into here so long as it can overcome the pressure on the capillary pressure versus saturation diagram. Right? So this is PC0. So long as the pressure here is larger than this point, then it will go into it. PC0 is a number. And so if we know the unit weight of the fluid, then we can calculate what the height would be that we'd have to increase this head to be able to physically go into the system. That's really all we're saying. So we can calculate that. So we know that if we know this value here, and we know what the unit weight of the fluid is, then we can calculate what this would be. So that's our first parameter to evaluate. So then the question is, how far would this ganglion go? And so one way to look at that is to look at the tip of this little finger and realize that at this tip there'll be a portion, so this is the tip of the finger, a portion which is the red fluid, a portion which is the wetting fluid outside it, and we can do the same kind of analysis we did before. If we go down all the way from the surface through this red fluid, and the pathway gets us all the way to this tip, then we can get the fluid pressure of this non-wetting fluid that acts here just by the height of this, the depth of this tip relative to the surface, multiplied by the unit weight. And so this is just going to be equal to H times the unit weight of the non-wetting fluid. But if we go to this point here, then we know that the pressure at this point in the blue fluid is going to be the same height, but it's going to be the height multiplied by the unit weight of the wetting fluid, water in this particular case. It doesn't care that there's a porous medium there and it's going through the pore space. It's just the same as if it's in a swimming pool. And so for this front to advance, it has basically to do the same as we did here, and it actually has to overcome a small amount of pressure, which is in addition to its balanced pressure. So it has to overcome this entry pressure. And so the pressure it has to really overcome is the water pressure plus the entry pressure. And so for this to advance, the pressure inside here has to be greater than the water pressure resisting it and also the physical resistance in the porous medium that it feels as well. And so if we convert each of these into something that involves a height, then we can rewrite this expression out like this. And if we rearrange it in terms of the actual height here that we have in each of these two components, we end up with this expression here. And this expression basically says that once it's in the porous medium, not sitting on the surface as in the previous case, so once it's in the porous medium, then it will keep on advancing so long as this criterion is met. So as long as the height is bigger than this amount, this is a material property, right? This is actually the bubbling pressure, or equivalent to the bubbling pressure. So in other words, PC0 is equal to HC0 times the unit weight of the non-wetting fluid, I think, right? You can imagine this. So it's actually a material property. And the ratio of the densities, or the unit weights of the two fluids. And so what we can do is we can figure out what the minimum height would be for it to keep on going. And so the consequence of this is that if this little slither of material gets in the system and it's at least this large, then what it means is it'll just keep on going. It'll go like a snake, I guess. This portion at the top will retreat and go down. The portion at the bottom will advance and go forward. And it'll keep on doing that as long as it's still in the same porous medium, because it's basically supplying within this little finger, if you like, it's supplying enough excess gravity or weight to be able to physically push it down. And the only way that's going to stop doing that, if for some reason it necks out and it splits up into two smaller pieces. And each of those two smaller pieces is smaller than this minimum. So it's an interesting observation. Once you get it into the ground, because you have a tall enough magnitude that it goes into here, and this tall enough magnitude is equal to HC0. And once it's in here, then this will keep on moving. It won't stop in the same material until it either becomes less long than this by breaking into two, or becomes compacted by spreading out horizontally, or whatever. But it will keep going for those. So there are two important numbers. One that relates to kind of a physical material property. Again, another one that relates to the same physical property but has a multiplier attached to it, which is always less than 1. So in other words, this is always less than 1, so this number is always bigger than this number it took to get it into the porous medium in its first place. So if you get it into the system, it could stop, or depending on the conditions, it might keep on going. Okay? So that's the other consequence, I guess, that comes out of our understanding of capillary pressures. An important concept. And so also kind of shown here. So these are the two conditions that try and explain it. It seems almost contradictory, right? And the contradiction, I suppose, is that it takes this amount of height of the fluid to go into the system in the first place, but once it's in the system, it takes a larger amount to keep on going. And so why are these amounts different? Why is one larger than the other? And the rationale is, I think, this. One case is this. This is the 55-gallon drum sitting on the surface. And this is the amount that it takes to go, this is the amount that it takes to go into the surface. And that's because the water table is sitting here below it. And so the water pressure that's acting up here is just the resistance of this water pressure, which is 0. This has to be atmospheric, right? So this has to be P atmospheric pushing up. If you raise this level of water on the surface to some higher magnitude, like this, and so then you could imagine now that the ground surface actually starts at this location, right? Just like in this. So in other words, the groundwater the surface starts here with the water table here, and this is this thing that's trying to get in here. Then what is the difference between the upper diagram now and the lower diagram? Well, the difference is that now the pressure acting at this bottom is no longer atmospheric, but it's equal to the pressure of water, which is greater than the previous atmospheric pressure that was acting upwards. So the water pressure is larger that's resisting it, and so you have to have a higher height of this for it to be able to go into it. That's really the physical case. And so understand, the physics of what we're trying to do. So these two expressions are relatively important in that they define these two essential behaviors. Getting it into the system in the first place from the surface, and then allowing it to keep on going once you've got it in there. Okay. Won't talk about that. I think that's all we need to talk about. Wow, geez. We did the venometer last time, and we talked about experiments last time. So those are the principal concepts. So I'm not sure whether that makes sense or not, but just to go back to where we started off this is really the workflow. And the workflow is that we want to be able to physically understand something about this, what the saturation profiles are with depth, how they vary, what is the mechanism by which this might stop keeping on going, what is the mechanism by which this gets buoyed by the water table. We know that at microscale we know something about the mechanics of this because it varies with the sizes of the pore throats that are present. But typically we tend to be able to characterize it not in terms of the pore throats, but in terms of the average behavior for a piece of the soil or a piece of the aquifer, which defines what the invasion characteristics are. And if we know something about these capillary pressure versus saturation diagrams, either in actuality for a particular soil, or maybe in generality that are defined for some certain characteristics, behaviors, then we should be able to take this information, rationalize what the water table means and how fluid pressures change both below it and above it, and be able to convert this into understanding what these saturation profiles would be relative to this, which is really what we attempted to do when we did this calculation here. And so we're turning it from something which perhaps we might not be able to use very easily into a diagram which we think we can always get. If not in this exact form, we think we can always get it in terms of J is equal to a function of capillary pressure and other physical properties of our system, and saturation of water between 0 and 100%. And we know exactly what those ordinates are. We spat them out at the beginning of the class. 0.3, I think 0.1, and on the reverse curve 0.87. And so if we have these data, then we can make a curve that looks like this. and the distribution of saturations either above the water table or below the water table with another non-aqueous phase fluid invading it are merely done by basically taking this figure and stretching it. And we can stretch it because we know that capillary pressures are proportional to heights times unit weights of fluids. And in our particular case, I guess capillary pressures will also be equal to, a height or a depth multiplied by a unit weight of a non-wetting fluid minus the unit weight of the wetting fluid. The difference is in those densities, which is really what this difference in here represents. And so if we can link capillary pressure to this, then presumably, since we define a J function as this, you could rearrange this expression in terms of capillary pressure as a function of J on one side of the equation. And you can basically take this capillary pressure versus saturation curve, anchor it at the surface, and then physically stretch it so that it comes to the appropriate coordinates on the system. And that would be your saturation versus elevation profile that you'd have in your system. That's what we're trying to do. And that's basically one component, not maybe of the third assignment, not of the second assignment.